Ladies and gentlemen, good morning. I'm honored to speak at this conference. My name is Yantao. I'm from South University of Science and Technology. The topic of my paper is charging navigation for commercial electrical vehicle in considering traffic and current dynamics. The outline of my talk as follows: background, research framework, charging navigation model, and conclusion. Well, let's move to the first part of this topic. The motivation of the work like this, due to the advantage of emission reduction and energy sustainability, many countries are promoting the development of electrical vehicle (EV). However, the limited driving range makes the driver in range anxiety. Therefore, establish an effective EV charging navigation with a short queuing time and a low charging cost. It is of great significance to EV users. In previous work, the charging navigation is divided into two categories: slow charging and fast charging. On the one hand, they consider the operation of power network and the transportation network. On the other hand, they consider the drawing time and charging cost. But both the slow charge and fast charge, the energy consumption of EV is ignored. To address the problem, an accurate energy consumption model and a queue waiting model for EV are proposed. Let's move to the research framework. Two proposed charging navigation method is comparative of transportation network equipped with fast charging station (FCS) and a decision center. The RTS connected traffic information. The FCS collected steering information, including charging price, real-time EV queue. The decision center collected information and sent charging station recommendation to EV user. The charging navigation process is when the EV makes a charging request, the EV need to upload its expected SOC, battery capacity, and other information. Satisfying the SOC constraint, determination of a candidate FCS for every FCS according to the traffic flow theory and an electrical consumption model. The drawing cost is calculated, and the queuing time cost is calculated by use a dynamic queuing model, and then the decision center will choose FCS with minimized cost function and send effective charging navigation to EV user. The objective function of charging navigation model is shown in the following equation. It consists of three parts. The first part we call the drawing cost, mu times t root plus phi times e count, where the t root stands for the drawing time, e count stands for the energy consumption. Mu and phi are unit time cost coefficient and the electricity price. The second part we call the queuing time. Mu times t weight ij. A double-layer queuing model is developed to catch the dynamic feature. The last part we call the charging cost. It is calculated by TOU price and expected SOC. The operating objective is to minimize the charging cost and the total time cost of EV user. Route charging time can be calculated by the distance and speed, but the modeling process of drawing energy consumption is complicated. In previous work, the EV energy consumption is conventionally modeled as a simple linear function of distance or charging time. This is obviously inaccurate. Through the analyze the electrical energy conversion process of EV, we process an energy consumption model. It can be estimated by use a tracked Fox F. The F is equal to initiate force F rho plus friction resistant F grade plus ramp resistant F grade plus accelerator resistant Fl. It can be seen from this equation that the drawing energy consumption of the Youwei is related to the average vehicle speed, acceleration of the vehicle load, road inclination, and a motor section. For the auxiliary energy consumption, it refers to energy to air conditioner and other electrical appliances. We analyze the relationship between auxiliary energy consumption and the temperature through 7,600 EV energy consumption data collected. We found that the temperature is too high or too low will lead to the increase of the organized energy consumption. And then we analyze the drawing speed and the energy consumption of different routes. It can be observed from the right figure that the more congested the traffic flow of the route section, the lower the drawing speed of corresponding route. In addition, the energy consumption of EV doesn't always increase as the drawing speed continues to decrease. This confirms that the assumption of EV consumption as a linear function of travelling time is initiate. Finally, let's move to the research and analyze. An EV generator charging demand at a node 14 at 9 a.m. Three cases are considered. Case 1, the short distance. Case 2, minimize the travelling time. And case 3, the model navigation model. From the table 1, it can be seen that the case 1 and case 2 both ignore the Qilin time and charging price, result in an increase of 192 and 4% case 1 and 142 and 2% case 2 in charging Qilin time, comparing with case 3. From 10 and 11 a.m., a total of 14 EVs in the route network sent out the charging demands. The charging navigation results in 3 cases are shown. It can be seen from the left picture that the charging demands of FCS 10 and FCS 19 in case 1 and case 2 greatly exceed their capacity, while the rest of FCS are not yet saturated. In case 3, the number of the EV choose FCS 20 increase. The utilization rate charging facility is improved, and the charging cost of EV users are also reduced. This paper is development to faster charging navigation. Many simulations are conducted to related to proposed model. The results show that it can reduce the charging cost for use leverage congestion as well as balance the utilization of charging station. That's all. Thank you for your listening.